In this video, we're going to look at how we can use Python to simulate the motion of a ball within a box, and then at the physics of dropping balls stacked on one another. In the first simulation, a single ball bounces around the window, following the rules of projectile motion and Newton's law of restitution. In order to look at the motion of the ball, we have to split its velocity into its horizontal and vertical components. The horizontal component remains constant as long as it does not collide with the wall, while the vertical component accounts for the effect of gravity. With each call of the physics engine, the vertical component of the ball's velocity is adjusted. The equation for the vertical velocity is given by v equals u plus gt, where v is a new velocity to be calculated, u is the current vertical velocity, g is the acceleration of free fall, and t is the time interval which can be adjusted to control the speed of the simulation. The horizontal displacement is then adjusted using s equals vt, while the vertical displacement is adjusted using s equals vt plus half gt squared, the v's in the equation standing for the horizontal and vertical velocities respectively. To understand how a collision of the ball with the wall will affect the ball's motion, we will look at Newton's law of restitution. This states that the coefficient of restitution, E, equals speed of separation over speed of approach, where the coefficient of restitution is between 0 for a perfectly inelastic collision and 1 for a perfectly elastic collision. The simulation assumes that the walls are frictionless, so the component of the velocity parallel to the wall remains the same, but the component normal to the wall will change by E times, E being the coefficient of restitution again, and will be in the opposite direction. The simulation actually handles the collisions by placing the ball tangent to the wall when a collision is detected. Otherwise, the ball might not escape from the wall in a call of the physics engine, and the direction of the velocity normal to the wall will keep changing with each successive call, essentially causing the ball to get stuck to the wall. This minor fix means that over time, the ball will appear to gain kinetic energy if the coefficient of restitution is set to 1. Now we'll look at simulating some balls stacked on one another being dropped, which was inspired by a Physics Girls video, which I'll put a link to in the description. This simulation lets us explore some more concepts on top of the previous simulation. It's quite a nice demonstration of the principle of conservation of linear momentum. This states that in a specified direction in a closed system, the total linear momentum is constant. So for a collision between two particles, the momentum before the collision is equal to that after the collision. As linear momentum is the product of mass and velocity, we can form an equation to get the velocity of one of the particles after the collision. But there's a problem with this, and that's the equation tells you that you need the velocity of the other particle after the collision to work out the velocity of the particle you're interested in. It's not like you can just go into the future and get the velocity of the other particle to work out what the velocity of your particle is. That's because the equation for the principle of conservation of linear momentum doesn't account for the coefficient of restitution of the collision, i.e. how elastic it is. So we need to use Newton's law of restitution again. We can now eliminate the velocity of the other particle after the collision to get an equation for the velocity of the particle we're interested in terms of the quantities that we know. This is the equation used in the Python code. As momentum is a product of both mass and velocity, and we know it is conserved in a closed system in a specified direction, we can see why a smaller ball on top of a larger ball would bounce higher than the initial drop height. It's because, due to the comparatively high mass of the larger ball, more momentum is transferred to the smaller ball when they collide, and the smaller ball gains more momentum. But its mass does not change, so its velocity increases, so it can bounce higher. In the code, a collision between the balls is detected as a loop is written so that, for each ball, it is determined whether or not the ball above it is in contact with it, and if it is, their velocities are adjusted accordingly, as well as the above ball being placed so that it is just touching the ball below, like with the collisions in the other simulation. The simulation doesn't handle collisions between balls of a similar size too well with this method, but it's still good for demonstrating the transfer of momentum from a larger ball to a smaller ball. I hope that you found this video interesting. The Python code for both simulations is available through a link in the description, so feel free to download and develop them.